Thanks for giving a great segue into Sebastian's presentation, which is called Play It Again, Recovering Analog Audio from Degraded Tapes using Synchrotron X-rays. Sebastian is a physicist at the Paul Scherrer Institute in Switzerland. He grew up in Canada and earned his PhD in Germany, working on nanomagnetism. He currently uses X-rays to study the magnetic properties of materials at the nanoscale, about 1/100th of the width of a human hair. Sebastian's passion for audio recordings was inspired by his mother, a musician, and is supported by his background in physics. He's developing a technique that uses X-rays to recover signals from magnetic tapes, an idea sparked through discussions with the music industry, such as the Decca label, and his collaboration with Kelly Pribble. He also works closely with the Montreux Jazz Digital Project in Switzerland, the British Film Institute in the UK on preservation efforts. Sebastian has held research positions at Argonne National Laboratory, the Max Planck Institute, and ETH Zurich, and has published over 65 peer-reviewed papers. Welcome, Sebastian.
Well, thank you very much for the introduction, Yuri. Thanks a lot for having me here. In this context, I'm just a physicist who's very enthusiastic about music and in particular music preservation. So I would like to update you on our project, Play It Again, which officially started about 2 years ago. We actually started investigating this idea over 3 years ago, and the idea is to recover high fidelity audio, video, and data from degrading tapes using X-rays. So we actually started with analog audio because that's the easiest thing to start with, and this is what I'll show you today. So this is the Paul Scherrer Institute in Switzerland. We are Switzerland's largest research center for basic science with about 2,000 employees. And what you see here is we have a lot of large-scale facilities where thousands of users from all around the world come every year to do experiments. And you can see these facilities as very large microscopes that we use to actually investigate the properties of materials. And I'm at the Swiss light source, that's there on the right. So it's this donut-shaped structure that houses a synchrotron, so that's a particle accelerator that creates X-rays. And around this accelerator, you have 20 experiments where different properties of matter are being probed. And this is what a typical experiment would look like, just to give you an idea of the sizes and the equipment we use. So this is my team for the project. So Jack is actually a postdoctoral researcher. He's a physicist. Lars is our engineer. Dominic is our technician. And Joao, Simone, and Joyce are master students. And we have collaborators within the Paul Scherrer Institute and also at synchrotrons all over Europe, in France, in Italy, and in Poland. And we're founded by the Swiss National Science Foundation, InnoSwiss, and also the UBS Culture Foundation. So you might, at this point, you might think, well, how did you get this crazy idea to use a synchrotron to actually read out tapes? And I have to say, we regularly measure magnetic materials using X-rays. And it all started with this experiment where we, back in 2017, we demonstrated X-ray magnetic tomography. So that's a micromagnet. It's a magnet like the one that would stick on your fridge, only this one you wouldn't see because it's so small, it's 10 times smaller than the width of a human hair. And what we did is we did tomography on this, and what you see here is essentially the magnetization within this very small magnet. So you see it's quite inhomogeneous. But that's not very important. This is just to say how it all started. And based on this, we published a very nice paper And this attracted a lot of attention, and about 6 months later, I got contacted by the head of R&D at Deca, who was an engineer back then, and basically, he wanted to know if we could do something with X-rays for all these decaying tapes they have in their vaults, or probably in Iron Mountain's vault. And essentially, it was through Decca and then through Universal Music that I got to know Kelly, and since then, we've been collaborating on looking at these issues that affect tape degradation. Yeah, so basically, you've all seen these. Through Kelly, I learned a lot about tape degradation and all the problems that can occur. Interestingly, everything he sees in North America is also present in Europe, so this seems to be a really international and pressing issue. And I also learned about the problem of equipment obsolescence. So the problem is obvious. If you have fragile tapes in a normal transport system or a normal player, you'd have to tension the tape, right? And then the head is in direct contact with the tape. So if it's fragile, that's a big problem. So this is where actually we bring in the X-rays, and X-rays meet, let's say, cultural heritage. But before we actually go there and I tell you how this works, I'd like to take a step back and go back into the structure of magnetic tape. So tape usually has 3 layers, so a MAC coat, a base film, and a back coat, which is optional. And if you look at the MAC coat, essentially the coat is made out of elongated magnetic particles that act as compass needles, and the magnetic information is stored in the magnetic orientation of these particles. So this is what it looks like when we look with a very good microscope, an electron microscope, and this is magnified 11,000 times, and now you see these particles there. If we zoom out, you see there's no particular structure. We can zoom out even more, and it actually looks fine. So now the question is, what happens in a sticky shed tape? What does that look like? This was, as scientists, this was our first question, and obviously we like looking at things on the microscopic level. So we got this MRL tape from '77. This was given to me by Richard Hess, and he said it had sticky shed. So as scientists, again, we wanted to double check this. So there's actually a publication that says that we can use infrared spectroscopy to actually check that a tape is unplayable. So there are certain fingerprints, specific peaks in the infrared spectrum that actually are telltale signs that this is non-playable. So we did the same thing on this tape, and we found exactly the same fingerprints. So this is definitely sticky shed. And this is what it looks like when you magnify. So it doesn't look very good. Magnify even more, so you have these dark puddles. So this is obviously the binder that migrates to the surface. And it's not just a binder. We actually see that there are micro cracks that develop. Of course, these are very small. They're on the micrometer scale. But this means that these tapes, even if you bake them, they do develop cracks and additional problems, and eventually they'll just fall apart. So the problem of sticky shed is well known, right? This is due to hydrolysis, where you have these polymer molecules that are broken into shorter polymers, and they become, well, essentially it's the same molecules that you would have in glue. So they're sticky, and this causes the tapes to shed. Now, heat treatment or baking is often used to temporarily remedy this binder degradation. And here we have, this is nothing, Kelly says it's amazing, and I say it's nothing revolutionary, but you see here as a function of temperature, you see all these puddles of binder on the surface, and then we increase the temperature. This is in Celsius. You would normally bake at 55, 54 degrees Celsius, and you see that already at 46, most of the binder has migrated back into the mag coat. So it's not absolutely necessary to heat up so much. So I'll just let this play. I just find it so interesting how at 46, everything happens at once, and the problem goes away, at least temporarily. All right. So here we actually partnered with David Aziz from the United Music Foundation in Geneva in Switzerland. And he had these Montreux Jazz Festival recordings that were on Pyral tape, CJ83. And the problem there is that these were produced in the late 1970s. So essentially with the economic crisis back then, it was very difficult to get certain materials. Either they were not available or they were actually very expensive. So what happens here is that the back coat sheds onto the mag coat. And what he developed is this flow that he published in the ARSC journal, where he cleans the tape. So he cleans, I don't know, 20 passes, then he bakes it for 15 days, then he cleans it again another 20, 30 times, and finally he can play it for 10 minutes, and then he has to clean the player head and guides again. So what we did here is we said, okay, let's see what this looks like on the microscopic scale, and this is again an electron microscopy image. So you see these chunks of back coat that are microscopic, but they are stuck onto the mag coat. When you clean it, you're essentially just smearing this. It doesn't really help very much. And then during the heat treatment, so we baked this tape for 30 hours, and that's kind of enough to have this back coat fragment melt and partially melt into the mag coat, but it's still not enough. That's why you have to clean it. And this is why he has to do this. So essentially, we tried to correlate what he had found with our microscopic understanding of the problem. So this is just understanding, and in the next step, what we want to do is actually just look microscopically and then determine which treatment will be optimal for individual tapes. And for this, we just need a very small piece of the tape. You can cut out, I don't know, a few millimeters of tape if it's possible, and we can do all the tests on that. We do crazier things too. We cut through the tape, so we have focused ion beam equipment where here you have a cross section through the tape. So you see the mag coat, the base film, and the back coat. On top you see like these sticky shed puddles. And we can also identify different materials. So you see the iron is mostly located in the mag coat. The oxygen is pretty much everywhere. And the carbon will be in the base film and the back coat. So here we're interested in knowing if the problem with the binder is just on the surface or is throughout the thickness of the mag coat. So, okay, coming back to the magnetic recording, how can you view the information? So here you have a magnetic viewer. I think most of you know this. And the idea is that the tape produces a magnetic field. Then you put this emulsion with iron filings in suspension, and they just basically aggregate around the fields, and this makes the patterns visible. Now we can go a step further and use an optical microscope and put actually, instead of this mag viewer with iron filings, a magnetic garnet. So that's a very soft magnetic material on top, and then use polarized light to have a look at the magnetic patterns that are imprinted. So that's a bit larger. It looks like this. Still fits in a lab. And this is what you see on the left. So you see where the garnet is. You see the patterns on the tape, and on the right, there's nothing, right? So this is actually a sticky shed tape. It's the MRL I showed you from 1977. And you see that the patterns are there. And then we can infer essentially the magnetic state of the tape. So essentially, it turns out that the data is still on the sticky shed tapes, which I think was quite clear. The the main problem is the mechanical fragility. So essentially, the tape can be read if there's little to no mechanical stress and nothing touches the surface. Okay, so how do we do it with X-rays? Maybe you know X-rays from your dentist's office. Well, we're not using this. The problem is that these kind of sources essentially radiate in all directions, and that's not good for us. So we rather use the synchrotron. Another great advantage of using the synchrotron is that the interior is much more exciting than your dentist's office. And this is what it looks like, essentially. So you have elementary particles called electrons that are accelerated close to the speed of light in this ring. And when they pass through specific types of magnets, X-rays get produced. And the nice thing is that we can focus these X-rays down to a few micrometers. And the particularity here is that we have a very intense focus beam. So these micrometers actually correspond to the size of the playhead gap, which means that we can read out the same frequencies as a playhead. An advantage, an additional bonus is that the energy of the X-rays is tuned to iron. So basically, it doesn't matter what you have on your tape. You can have a thick coat of paint covering the tape, as Kelly showed. It doesn't matter. We only read the iron. So this is a bit what it looks like. So essentially you have the synchrotron, there's a lot of technical beam shaping going on, and then the tape. So of course the original idea was like, can we do tomography on the tape, just read it, you know, just leaving it there without unwinding it. And it turns out that it's a physical limitation because the X-ray energy we need to read out the iron essentially is too low to go through an entire tape pack. So we need to unwind it. And that's why we're also looking in all these chemical processes and understanding what can help unbind tapes. But also there's a big advantage that the tape doesn't need to be playable. So if it's full of MAC coat, if it's full of debris on top, or the back coat was sticking on it and so on, it doesn't matter because the X-rays just go through everything. So this is what our player looks like. Quite compact. So on the right you have the shaped X-rays that get focused essentially here in a box. Of course we don't need all this equipment, so this is one of the 20 beam lines I showed you. And many users come here and they have different experiments and needs, so there's a lot of equipment. What we're actually using, so you see here how the X-rays come out of the focusing optics, and they go through the tape. So we started for a proof of concept just with segments of tape that come from a larger spool, and basically then we measure the transmitted X-rays with a detector. So what does this look like in concretely? So essentially this is a quarter-inch track, quarter-inch tape with 2 tracks, and we have the slit-shaped beam that's about 1/10 of the width of a playhead. So you see here it has, the width of it is 4 micrometers, and it spans 200 micrometers, so that's 1/10 of the width of the track. The advantage of this technique is that it's extremely sensitive, so we can extract the information that's in single grains, so that would be enough for us to know what's on the tape. And this is what it looks like. So essentially in blue you have the Studer output, and in gray our X-ray signal, which is kind of noisy, but this is due essentially to the particulate nature of the magnetic coat. And of course then we can process this, and then we get the orange curve, and then we get, depending on how you process it, pretty good, very good agreement even with what's on the tape. So I don't know if this will play, so what I want to show you is a 1 kilohertz tone. This should play? Okay, yeah. And that's then the spectrogram, so it's just to show, okay, we recorded 1 kilohertz on new tape, and then we have this sticky shed tape that had a lot of tones on it, so that's 1 kilohertz from there. It also works very well. Here's a frequency sweep. So on top you have the Studer A20 output, and on the bottom the X-ray signal. That's the raw data, which already looks pretty good. We can, of course, process it a bit. Looks even better. All these recordings were done by the Swiss National Sound Archives that we're working with. And here you see a frequency sweep, 50 hertz to 1,000 hertz. And you see that there are some notable differences. So one of them is, of course, the EQ. So there's no EQ in the raw signal. So essentially, the intensity of the signal will go down as a function of frequency. And then you see this jump here also in the Studer, and that's when you press play. There's a capacitor that charges and then eventually discharges. So the main differences actually come from the electronics of the tape player, because we're, of course, reading out the raw signal that's on the tape. So that was a good tape. Now, let me show you a physically damaged tape. So essentially, this is a tape where at the Swiss National Sound Archives, they recorded test tones as well. And then they took it, they stepped on it, they stretched it, they heated it, did all sorts of things. And you see here, there's this kind of fold there and a lot of scratches, and when you look in a microscope, just an optical microscope, you see them, and then as the playhead passes over, it averages, of course, all of this, and then you get distortion in the signal. So our first question was, well, is the signal really damaged or not, right? Or is it just some kind of averaging effect? So with the Kerr microscope I showed you before, we had a look here, and here you see a portion of the track exactly where these folds are. And you see that one of them is very local, it's not a big problem, but the bottom one actually leads to the magnetic signal to be washed out. So what we did with the X-rays, we went through this and took along two cut lines to see what we get with the X-rays. And so this is the Studer, that's the X-rays, absolutely no variation, and that's the second cut line, also no variation. And the reason for this is essentially that with the X-rays, we don't just measure the magnetization, but we also measure the amount of iron. So here's a map of the amount of iron throughout the thickness of the tape across these two folds. So you see that there are large variations in iron. And then when we calculate the magnetic signal, we actually divide by that, or we compensate for it, so that's why we get the full magnetic signal. And no other technique can do this, because the X-rays penetrate throughout the entire thickness of the tape, and yeah, also we measure the amount of iron. So here you have a map of a period of the track. You see that is distorted, and that's because the tape was actually physically distorted, was crumpled, right? So here we recovered the signal, and yeah, then you see the spectrogram. So I got a couple of questions last night. How far up in frequency can you measure, right? Oh, okay, so that's actually the other slide. I'll get back to that. So this is, I want to show you delaminated tape. That's the same MRL from 1977. That sticky shed at some point in the center. It really started to delaminate. It was pretty bad. I didn't know, this was my first experience. I just started hearing crack, 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 and I had no idea what was happening until I realized. And essentially now we can look at it very carefully and just focus on one of the regions, and then with the X-rays we can measure essentially the magnetic signal around these regions which are damaged, where the magnetic coat was had delaminated. And this was a 500 hertz tone, so we could recover the tone without any problem. Okay, and here comes the how high can we go in frequency. So this is a frequency sweep we measured. You see this is not the raw data. This is then processed and equalized. And here you have the spectrogram. So you see that the Fourier transform intensity goes up to about 18 kilohertz. So this we can do routinely. And then you have in the spectrogram some artifacts at the beginning and at the end. That's because the sweep is 25 milliseconds, so this is kind of unavoidable. And then you have this artifact in the center, and that's because we changed the sampling rate in the middle of the measurement, which wasn't, in retrospect, too smart, but, well, it proves the point. But, okay, this is routine. But we focused the beam also down to 200 nanometers, so that's 0.2 micrometers. A typical playhead would be 3 to 4 micrometers, and we can actually get an equivalent sampling frequency of 2 to 3,000 kilohertz. So essentially, we get all the information you'll ever need off the tape. Of course, we don't want to just be stuck at looking at small pieces of tape, so we're building a tape transport mechanism, and it's a zero-loop transport, right? So one of the difficulties is actually maintaining the angle of the tape with respect to the X-ray beam, so that's why we have these two linear stages, and here you see it in action. So this would be the direction of the X-rays, and essentially we have distance sensors that detect the size of the two spools, and it only starts rotating once it's at the right angle. So we have our own Studer A80 for tests and for recording tones and testing. So this is a loan from Studio Ide und Klang in Basel. So this is the studio founded by the sound engineer Daniel Detvila. And essentially, he specializes in analog audio, so everything he does is analog. And we were lucky that we got one of his Studers. In terms of partners, we work with Memoriav, so this is the Swiss competency for the preservation of cultural heritage, audiovisual cultural heritage. We work with the Swiss National Sound Archives, with the Montreux Jazz Digital Project and the Montreux Jazz Festival, of course with Kelly, with the British Film Institute, NOAA Archive, Richard Hess as well, and yeah, I mentioned, so David and Daniel. We have from the Montreux Jazz Festival this B.B. King recording from his 1980 concert. So this was his second concert in Montreux. It's also on one of these spiral tapes recorded in Nagra Master. And this is where the back coat is essentially disintegrating. And this, here you see from David's tests, basically you see all the black deposit right on the roller there. And this will be the first demonstration of our technique on, beyond test tones and frequency sweeps. We've also been a bit in the media. So there was a press release put out by PSI, and then we were on Swiss radio and TV, on the night news, in Blick, which is a bit like in the German part of Europe, it's a bit like USA Today. And in Die Welt, which is even more known. And I even got contacted by SMPTE because they were quite curious to know what this was about and how it works. Okay, so in conclusion, we demonstrated that we can read the signal recorded in magnetic tape using X-rays. The readout is touchless. It doesn't, so in that respect, it doesn't damage fragile tapes. The tension also needs to be very low. We have a depth of field for the X-rays of a few millimeters, so even if you have a tape that's crumpled and so on, it doesn't matter. It will still be in focus, and we can read out physically damaged tapes. So we want to explore the potential of the technique, also the interest of the community and what we can actually bring, and develop this as a viable solution for the recovery of degraded audiovisual heritage, but really like what Kelly showed, very degraded audiovisual heritage. The principle is, of course, applicable to all tape formats. And yeah, we're aiming for real-time readout or almost real-time. And we're also developing signal processing software, which is unique, of course, unique to this technique, where it has its own set of sources of uncertainty and noise and different distortions of the signal. Now, this was the X-rays. I just want to show very quickly that we're not just looking at X-rays. We want something to have a more comprehensive picture. So essentially, another possibility we're looking at are magnetic sensors. So this is the kind of sensors you have in a hard drive. And here we partnered with Inest. This is in Portugal. And they are experts at essentially fabricating these kinds of sensors. The technology behind, the physics behind this technology was awarded a Nobel Prize back in 2007. One of the recipients was Peter Grünberg in Germany. And the reason I mention this is that during my PhD, I actually worked with this group, so I knew Peter very well. And the people at Inest were actually the first people who brought magnetoresistive sensors to tape playheads over 20 years ago. And this is the setup, so they have all the know-how and the technology, and they resuscitated it. So this is quite a crude setup here, where you see the tape on just lying there and basically being scanned. And here's a comparison between the sensors and the Studer output. And the nice thing here is that you're not touching the tape. You're also at a certain distance from the tape. So the idea is our goal is to develop comprehensive solutions, including chemical, physical analysis, using synchrotron X-rays, and other types of sensors and possibilities to extract essentially the raw signal from tapes. So with this, I thank you very much. Is that too long? Good.
Yeah, thank you both so much. We do want to open up to questions. Thanks for taking us down a really depressing hole at first and then giving us some hope. All I could hear in my head was the great Dietrich Schuler saying, "We are up against an ever-decreasing time window." Those of you from YASA know that quote very well. I could just hear him saying it over and over in my head as you were showing all of the pictures. Bill, do we have any questions over Zoom?
Yeah, there's a few things. Dave notes that we've experienced something similar with a collection that came from the coast of Seattle, blue paint from the box from the 60s. I've seen white paint as well, actually.
So is that a question or is that a comment?
This is a comment. But
Okay.
Next up.
Somebody else is seeing it besides me. Great.
Yeah, I've seen it too, actually.
Thanks. Great. Anybody else in the room seen this before? No. Fair enough.
We've got a question that can maybe open us up to a discussion of the nature of a potential distinction between soft binder, loss of lubricant, sticky shed, what that might be, and also what's going on with the total destruction of these Ampex 406s. The question is this: for loss of lubricant tapes, are you baking your tapes? We have been able to drastically reduce the effect of loss of lubricant by baking for 24 hours at 125 degrees Fahrenheit. This is primarily for Ampex 406, 407, and 456, 457 quarter-inch tapes. Just curious what other preventative methods you're using before or after attempting to clean.
Kind of loaded question there. I have not found, particularly on 2-inch tapes, that baking improves it, and we have to still clean it a lot of times. I'm getting a lot more of these tapes, so the jury's still out. We're still trying to get techniques and figure this out as well. I've had people tell me to bake a tape for 2 or 3 weeks. That killed the tape, in my opinion. It got so dry that it wouldn't move across the heads. It squealed. It stopped, particularly when you're dealing with 2-inch. Quarter-inch is a little more forgiving, but when you get a 2-inch wide tape that there's no more lubricant left or you've dried it out so much, it won't play. And when I was in Brazil, I actually brought this up to an individual, and he said, bake it, bake it, bake it. Baking solves everything. I can tell you this, it does not. And I had to go the opposite way to get tapes unbound. So baking did not cure it whatsoever. In fact, it kind of hurt it a little bit because it made the lubricant even drier. And once I started peeling it off, then the tape started disintegrating. So actually baking actually hurt the tapes more that were bound than helped them, in just at least what I've seen so far.
Can I add something? So in our experience, when lubricant comes to the surface from the electron microscopy images, so we've actually also had the chance to have a look at some of these tapes, and basically we saw these very nice formations that look like crystals, like flowers of a crystal on top, and this is the lubricant. And it just doesn't melt when you bake, so it doesn't melt, it doesn't go anywhere, it just sits there. So yeah, I don't think baking is a solution, but I don't have any at the moment.
We're bringing a microphone.
Thank you. One person you mentioned in the Swiss world that you live in is Stefano. And that's a name that's familiar to a number of us. He was actually on our technical committee for a while. I'm curious, I know he kind of is retired and gone his own way, but if you interacted with him, it would be interesting to know, because he is he's presented here at ARSC before, and any input he gave you or vice versa.
Yeah, so actually we were lucky because he was very enthusiastic about this. He was one of the first people I talked to, and he really was very supportive. And of course, I was maybe a bit naive at the beginning. I said, oh, we'll read the analog waveform, and that'll be it, that'll be easy. And he said, no, I don't think it's that easy, because he spent, a long time with this disk scanning technology, right? So he was right. It's not that easy and straightforward, but yeah, he was very enthusiastic. He was one of the first people I actually talked to, and all the recordings we had, all the test recordings, are done by the Swiss National Sound Archives. So he really helped us out a lot. Yeah.
I highly encourage everyone to look up the recordings of Stefano's presentations on visual audio.
Just want to say that I think this is amazing, Sebastian, what you guys have been doing. Oh, yeah, sorry. Mastering engineer, microphone, have no idea what to do with it. When one doesn't have access to a particle accelerator,
No, everybody does now, right?
how do you see this, developing as a business line or as a product or what have you? Obviously, time in a particle accelerator is expensive. Building your own is prohibitive. So I imagine you have some kind of thoughts as to how this might become a bit more practical in the future.
Yeah. So essentially, yeah, the particle accelerators are pretty expensive, but they're becoming less and less exotic, so to speak. So even Intel was considering building one to produce these chips with sub-10 nanometer features. And the reason is that today, they have to buy these huge devices to do this, and one of them costs 100 million, and a synchrotron is also about 100 million. And there you get 20 beamlines, so you get 20 times the productivity, right? So I would argue they're becoming less and less exotic, and there are about 24 synchrotrons in the whole world. So the technology we're developing is actually compatible with about a dozen of them, and it can be in principle then replicated, right? So I worked at Argonne National Lab. There's a synchrotron. There's one in Berkeley, one in Stanford. So I would say there's enough around the world to meet local demand, right? Right. On the other hand, sure, it's expensive. The faster we read out, the less expensive it gets. I would say, sure, it's for the BB King tape, I would say that will cost about 50K for the first tape, right? But you can imagine it's really for recovering the unrecoverable. So if you have great artists, right, and that's the last chance, then it's definitely worth it. But it's not for your whole home collection, or not yet, at least.
Good question here. Fantastic fantastic presentations from both of you. Kelly, have you tried your adhesion cure for older Scotch 201 syndrome tapes?
Yeah, we've actually had it with that as well. The crazy thing about the adhesion syndrome, I didn't see it until the Bruce Springsteen, the Bob Dylan stuff came. We thought it was regional to South America. I saw it all over South America. We thought it was regional. Every Ampex 2-inch 456 tape I could find in Brazil had adhesion syndrome. And we thought, well, maybe it's a manufacturing just that was sold here. We didn't know why we saw it down there only. I literally, for several years, thought it was only to regional South America until the Bob Dylan collection came in, and I had 63 2-inch tapes that had the same issues I had been seeing. And then I basically just applied the same principles I was doing there. But then by then, I'd learned quite a bit more. I was able to build a machine. I was able to do things I couldn't do down there. But we're starting to see other brands doing it as well. And they're starting to see French brands doing it over in Europe. So it's not a one brand issue anymore. We thought it was for many years. And we're starting to see it with Scotch, starting to see it with Agfa. And I just think it's the process of the manufacturing as it's getting old, starting to develop new problems. Basically like the leader tape, no one ever expected 3M to have a product that all of a sudden is starting to degrade and starting to pull the oxide off. It's, as we're seeing time go by on all these tapes, or, from the 70s and 80s, new things are starting to develop, which is a little scary, to be honest with you, because we never thought the leader tape would ever do anything until 2 or 3 years ago, and now we're seeing it a lot now. And so we're able to apply the same process to multiple brands. It's just that one 406 quarter-inch from the mid-70s, the delamination is happening a lot more. Right. And it's more on quarter-inch than it is the wider. We don't know why yet, but as we're working together, we're going to try to figure out, once we see one, put the particles together, send it to these guys, let them do some analysis on it, and try to figure out why it's happening. Is it preventable? Because we know the binder's just no longer there. We don't know why it's no longer there. We don't know why it's not sticking, but we're going to try to figure it out as soon as we can, because preventative is everything if we can.
Well, have you seen this unique to back-coated polyester tapes, or are you doing this just with...
I've seen binding with acetate starting to creep up.
Right.
And here's the problem. Acetate and normal polyester tape do not like the same process whatsoever. Okay. Acetate, I'm actually coming up with a new process for acetate because it will shrink. And actually, I'll tell you, the same process I use for acetate, I didn't know it. It's a wet soak process. It takes time. It actually shrank, and the whole tape became a bowl, and it actually bent the metal flanges in the shape of a bowl. That's pretty strong, and I couldn't push it back down. And then as I start unwinding the tape is curved because the inside of the tape is shorter than the outside of the tape. Instead of being a straight tape, it's curved, and acetate's starting to do that. So, I'm the only guy at Iron Mountain doing this globally. When my machine gets, readily available, we'll be able to clean tapes elsewhere. But I'm in New Jersey, so everything's coming to me. I've got a lab, which, I'm limited to what I have until I meet this guy, which, now I get to send stuff to him, and he's way better at figuring out what's going than I am. But the collaboration is, we're just trying to preserve history. We're trying to preserve music because we're both music nerds. We're both history buffs. And we're just trying our best to figure out, before we lose this stuff, if we can save it at least, or get one more play out of it. And sometimes we're losing. So I hope that answered your question.
Thank you.
I know you had a question.
We could be here all night, but does your Cinetech cleaner have an ADAT adapter? No.
Not yet. I'm actually, the machine that was my prototype that I've taken the cassettes out, I'm actually going to build a better machine to do that, because with videotape or cassette-based tapes, we're starting to see mold, because we digitize video as well as audio. We're starting to see a lot of tapes come in with mold. My biggest challenge is every one of these different digital tapes or cassette-based tapes has a different sprocket. So now I'm having to build different adapters per machine or per tape. And I got a D2 the other day that's a completely different sprocket. So now I got to go build a new adapter just to be able to clean those tapes on that little machine. So I'm going to get a better machine to do that. So far, the only way, in my opinion, is with the conventional cleaners that you can put a cassette in with the tape inside, it's going to clean it and just recontaminate it. So I'm having to take the tape out of the cassette to get the mold completely removed from it. I haven't figured out a better way to do that yet. Maybe in a couple of years, maybe we'll have a better way of doing it. But right now, it's a very manual, physical approach. But people are paying for it because some of these videos or some of these ADATs are one of a kind. There's no copies. And particularly ADATs, they're a nightmare. They're a nightmare to digitize, let alone 9 of them stacked together for one show is a nightmare. So future's looking bright, but we're trying to challenge everything as we get it. And it's not easy. And like I said, I'm having to develop or build on the spot basically what I need to do. And it's, with the new machine, with the Cinetech machine, that's going to be miles ahead of me standing there with a handheld cleaner. And we just got to make sure the tape is safe enough to put on there and be able to actually clean mold. Or a lot of tapes we're getting the clients, particularly video, like a 2-inch quad or a 1-inch video, they want the tapes clean before we digitize them. And that machine will be able to do that. So hopefully that's kind of the future of preservation for open reel tapes, is hopefully where I'm trying to be.
Yeah, truly amazing. Question I have is I see your Deca beginning there, and I think about how we used to do a lot of editing, especially in classical music. How does your system accommodate all those edits when everything's degraded? Has that something you've touched upon yet? I know you got to start probably with something not so complex, but it certainly is a thing, and I know in that archive there's going to be a lot of that, of like these original edit masters.
Yeah, so that's a very good point. So we haven't looked at tape with edit splices, right? What I can say so far is that for the X-rays, like I said, the splicing tape makes no difference. So nothing will push out the tape like the VHS players, right? So I haven't done it yet, right? So I've been naive before and said, oh, this will be easy. So I'll just say I don't know, but my first thought is, if there's some splicing tape in there, it shouldn't change anything because. Oh, okay. Right. Yeah.
It's disintegrating, or it's coming. Yeah.
Right.
Unknown at the time. Do you have a suggestion? True.
So actually, we had this crazy idea that, for example, these tapes, right, that Kelly showed that are falling apart, right, that we could cover it with something like a polymer, right? So it's kind of, you just put something on top, and it's like putting cement around something, right, just to keep the structural integrity. And we put this layer of polymer on top, and that fixes the tape. And for the X-rays, that's not a problem because it goes through everything, right? I mean, a normal playhead would have a problem because now you're far from the tape, you're missing probably the high frequencies and so on. But for the X-rays, it doesn't matter. So that would be a possibility, but I haven't tried it, so.
I just have a comment that this is really amazing technology that, in looking ahead, if you would be able to gather all information from the tape, and then you can apply it back to the tape. So you can record it. We talked about it before.
Yes,
so
exactly.
This is an amazing future that it would be restored in analog format, and with all this information that you've been reading. Yeah, thank you.
Yeah, thank you. That's a very good point, yes.
Thank you. Kelly, a question about the cleaner. I noticed you have the air blade. Is that strictly for your wet process, or does it also do some abrading? Do you have a burnisher, for example?
No, there's no burnisher. And one of the things for the blade is, one of the things I designed that I actually didn't talk about was with the palon going around the cylinder that is actually the tape goes across, we're actually sucking from the backside of the palon through a filter, recirculating the air that then goes to the air blade. So we're actually recycling the air twice. It goes through a filter. We're sucking away as much particles as we can on the backside of the palon. The palon we're using right now is very thick. We're trying to figure out a manufacturer to get it a little thinner so we can actually suck through more of the palon. But we're trying to, there's air blades that are blowing, and there's actually suction vacuum in the process of the tape path as well. So it's something that, we're trying to design, we're trying to figure out. When I built this machine and designed it with these guys, they had no idea. I was speaking Chinese to them about what I wanted to do because they do a film. And so they don't know anything about magnetic tape and all the intricacies with magnetic fields and motors and things like that. And so now it's up to me to really develop and refine the machine to do what I needed to do. It just arrived in my studio, my lab 3 weeks ago. And so I'm still just in the beginning stages of figuring out what to do with it, what's the best process. The biggest thing I've got to do now is really, with 1/4 inch and 1/2 inch and the different thicknesses of 1 mil or 1.5 mil, is to set up presets of the tension on the machine. So I'll have a preset that says I'm doing a 1/4 inch tape. It's going to ask you, is it 1 mil or 1.5 mil? And hopefully we'll be able to know the tension settings for the different thicknesses plus the widths. I've got a lot ahead of me to develop all that, to be honest with you, but I'm hoping to have that done within months. And I just got the rollers being sent to me for 1/4 inch and 1/2 inch yesterday. So it's a little bit of a time consumption on getting this and perfecting it. I'm not going to put it out, or we're not going to put it out until everything's perfected. We know it's not going to damage tapes. We know it's going to erase tapes. There's a little bit of a hill to climb, to be honest with you, but this is my first machine that will do multiple formats, and I don't have to be there. Iron Man keeps saying, we want to clone you, we want to clone you. Well, these guys that probably could clone me, but that cloning me is that machine right now, because it's basically developed to do all the hand techniques that I do manually. That is going to be hopefully automated, that I can send one to California on the East Coast. I can send one to the UK. If we have an on-site project that the tapes can't be sent to us. I'm dealing with this project in the Appalachian Mountains called Apple Shop. I don't know if anybody's seen this, where this flood came through 2 summers ago, and there's 13,000 tapes that are completely covered with mud. I developed a machine to actually liquefy the mud very quickly and bring it away from the tape. They had funding through FEMA, and we were going to start the project this year. Unfortunately, the FEMA grant was pulled away, and now there's no funding. So the process of educating and me developing new machines was based on those grants. And that grant got pulled politically for whatever reason. We can all guess probably why, but that funding just went away. Those people are devastated because that funding was to procure their legacy and their history of the Appalachian people. And there's thousands and thousands and thousands of these tapes completely covered with mud and completely covered with mold. It's audio, video, and film. And so as I'm trying to develop new techniques and new machines, there's a cost factor there. We got to be funded somehow. He's being funded through grants, things like that. We're looking at that. But I got to be honest with you, in today's environment, getting money for grants is almost impossible. And we all know why, and we all can figure out why, but it's going to be a time test to see if we can get funding to be able to preserve this historical content that unfortunately is going to go away. And the Appalachian project is something I'm very personally involved in. It means something to me. So now I got to figure out how I'm going to do it without funding or be able to raise funding. And I know I was in Nashville for many years. So I'm trying to see if we can do some concerts or something to raise money for these people, because we're going to lose the history of these people, which is vitally important to our country.
And what's your opinion of the burnishing, if I could?
I've never used it, to be honest with you. I'm a little afraid of it because I've not really had much experience with that. I'm not afraid of it to start trying, but I just have not been around it yet.
Okay, thank you.
Thank you all for your great questions. Thank you, Sebastian and Kelly. I want to let us go so we can get ready for our visit to Church Studios. Both of these gentlemen will be there, so you can continue asking them questions during the cocktail hour. Thank you for a great first day. See you tomorrow.
Thank you guys for coming. It really means a lot to us. It really does. Thank you.